Okay, chapter 3. So moving on from truth tables and so on, we're going to be exploring a different way to show validity for an argument. This is going to be, in some ways, complicated, but a lot less labor intensive compared to a truth table, and I think in some ways more fun. These are more like puzzles. All right. So in this chapter, we got a couple of things. In this video, we're going to be talking about 3.1 and 3.2, the rules of inference. This week, we're also doing 3.3 and 3.4, the rules of equivalence. Do some practice with derivations. We're not doing 3.6, the biconditional. There's some special rules that the textbook gives you that apply to the biconditional, but these are kind of redundant and I think end up just complicating things. So we're going to skip that. You don't need to read section 3.6. And then in the week after that, we'll be doing conditional proofs and indirect proofs. And your second exam is going to cover all of this content. It's just going to be chapter 3. But there's plenty in chapter 3 for an exam on its own. All right. So starting with inferences. So arguments in propositional logic can be tested for validity semantically, which means by a truth table. We can see if there's any row in a truth table where all of the premises are true and the argument is, or in the conclusion is false. And if that was the case, then it would be an invalid argument. But they can also be tested proof theoretically by means of a derivation or a proof, which is what we're going to explore doing in this chapter. So a derivation, or proof, is a sequence of formulas, every member of which is an assumed premise, or follows from earlier formulas in the sequence according to rules. So basically what we're going to be doing is we're starting with our premises and our conclusion, uh, just as we did when we would set up a truth table, but instead of setting up a truth table, all of the possible truth values for um, the major operators of the premise and the conclusion, etc., we're going to just assume that the premises are true and see if using only those premises and the rules of inference and equivalence that we'll introduce here, uh, we can manipulate those premises so that we arrive at the conclusion that we're interested in. Now, if we can do that while following all of those rules and not making any mistakes and so on, then it would seem that the conclusion that we're interested in showing is actually entailed by the premises that we're given. So that if these premises are true, then this conclusion has to be true. Okay. Um, so a system of inference is a set of specified rules for derivations. We can't just do anything. Of course, we're going to be constrained in certain ways. Some of these rules will be obvious. Some of them are a little bit less intuitive, but we'll try to talk through those. Um, and the rules tell us basically how to get new well-formed formulas from the old ones. And here, this is where you'll start to see sort of the power of being able to put things in a symbolic logical form, because some of the conclusions that we're able to get to by putting things in a strictly formal system and applying the rules correctly are less intuitive than we'd be able to get to otherwise. And they allow us to arrive at something new that we may not have expected was entailed in the premises that we're given. So our system of inference for propositional logic has two types of rules. First is rules of inference, which is how to get from one thing to another, valid argument forms, and rules of equivalence, which is also is in some sense going from one thing to another. But a rule of equivalence is going to be a way to substitute a well-formed formula with another well-formed formula that is logically equivalent to it. Now, because it's logically equivalent, they're fully substitutable for one another. And sometimes it'll be easier for us to work with a logically equivalent formula that has one form rather than another form, so we might want to swap them back and forth, which is why rules of equivalence are helpful. So first we'll be starting with uh, rules of inference, and then we'll be talking about rules of equivalence. So the system of inference is complete. Every valid argument and logical truth will be provable if our system of inference is complete. If our system of inference is sound, every provable argument will be semantically valid. So every provable proposition will be logically true. And our system of inference for propositional logic will be both complete and sound. All right, so first rule of inference, modus ponens, and we're going to use MP. You'll see when we do a proof, we're going to want to show what lines we used as a justification for that proof, and then we're going to want to show what rule we applied to those lines in order to get the new premise that we're getting to. So we'll use NP in any instance of modus ponens. So modus ponens is known as affirming the antecedent, since the second premise affirms the antecedent of the conditional in the first premise. So you can see this works pretty simply. We need two things in order to apply modus ponens. First, we need a conditional. Some conditional. Here we have if alpha, then beta. Remember, the Greek letters stand for any well-formed formula. They don't have to be just an A or a B. It could be any well-formed formula on either side of this conditional. It could be very complicated, very simple, any well-formed formula. So first, if we know that it's true that if alpha, then beta, remember this conditional is expressing a relation between alpha and beta such that if alpha is true, beta must be true. And our second premise is alpha. In this case, we know alpha is true. We're assuming alpha is true. Then it must be the case that beta is true. Because it is true that if alpha, then beta, and there is an alpha, then there must be a beta. So we're able to arrive at the conclusion beta from, we need two things. We need the relation between alpha and beta described by the conditional, and we need the material of the antecedent, alpha. And if we have the antecedent, and it's true that the relation between the antecedent and the consequent is a material implication like this, then it's true that beta. So and you can check the validity of modus ponens or any of the rules of inference on rules of equivalence by just going and putting everything in a truth table. If you want to, if you're curious, you can sort of reveal the structure to yourself in this way. With some of the rules of equivalence, it might be helpful to do this to kind of think through how things are equivalent, especially in cases where it's not obvious. But so here we're going to have, we have our base columns here with S and P. We have two variables, so we're going to have 4 rows. We can see that S is listed as true, true, false, false, and P is going to be true, false, true, false. Go ahead and fill in S and P everywhere. And here we can see that in every row where both of the premises are true, then the conclusion is also true. So the validity of the rule of inference can be checked where we know that if we have the first the rule if S then P, and second we have the antecedent of that conditional, then we can conclude the consequent. All right. So a substitution instance is a set of well-formed formulas of propositional logic that match the form of an original rule. So here is an example. We have a substitution instance of modus ponens. So here we can see that instead of alpha and beta, we have some other well-formed formulas. Instead of alpha, we have S and not P, and instead of beta, we have Q if and only if T. But we can see that when the second line, we're given the entire antecedent, and remember, we're going to need the entire antecedent, whatever the antecedent is. So first, in the first premise, we can see if it's the case that S and not P, then it's the case that Q if and only if T. And our second premise says, well, S and not P, so we can conclude, therefore, Q if and only if T. So exactly the same thing as just this form of modus ponens that we've been given, but instead of the alpha and beta, we're working with some other formulas. So here's another example. This is an even more complex, well-formed formula. So we can see on the left here, we have the antecedent is going to be this disjunction between S and not P, or if R then C. Then the consequent is going to be this double biconditional here, which is going to be Q if and only if T, if and only if not D. Hanging an extra bracket there, this should just be a regular parentheses, don't worry about that. But this is just showing that whatever it is, if we have the entire antecedent, we can conclude the entire consequent of a conditional that we're given. All right, so this is something to be careful of. This is a logical fallacy called affirming the consequent, where if we have a relation, if alpha then beta, we cannot conclude alpha from being given beta. Remember, there's only one situation in which, think about the truth tables for a conditional. It's possible for the consequent to be true and the antecedent to be false. That does not invalidate the conditional whatsoever. A conditional can be true when the consequent is true and the antecedent is false. If we think, instead of if alpha then beta, we think about if it rains, the earth will get wet. Well, the earth could get wet without it raining. That's not a problem. But when we're saying if it rains, the earth will get wet, we're saying if it rains, then certainly it's the case that the earth gets wet. So the earth getting wet always has to be the case if it rained. But the earth can be wet without it raining. It can be wet for other reasons. You can spill water on the earth. There are all sorts of reasons the earth could be wet. So just because we have the consequent doesn't mean that the antecedent was present. So we can't conclude from a consequent that the antecedent is true. So be careful about this. And conditionals, again, are going to be some of the trickier things to work with here. So keep this in mind. All right, so here we have another rule of inference that works with conditional. Instead of modus ponens, this is modus tollens, a rule of inference with the form if alpha then beta, we're starting in the same way. But in this case, our second premise is not beta. And we can conclude from these two premises, first, the relation if alpha then beta, and secondly, from knowing not beta, that not alpha. And this is because, well, we know that if there was an alpha, then there must be a beta. Because the relation is saying if alpha, then beta. And we know there's no beta, which means there cannot be an alpha, because if there was an alpha, according to the first premise, then there would be a beta. So because there's no beta, we can conclude no alpha. So sometimes known as denying the consequence, if we have a relation between an antecedent and a consequent here, this material implication, if alpha then beta, and we know that it's not the case that beta, we deny the consequent, then this allows us to deny the antecedent. Or not deny the antecedent, but we can conclude that the antecedent is not present. All right. So the reason why I backtracked to saying denying the antecedent is because denying the antecedent is actually the name of this fallacy here, which is going to be kind of the inverse of the first fallacy of affirming the consequent. If we have the relation if alpha then beta, and we know that it's not the case that alpha, then we cannot conclude that it's not the case that beta, for the same reasons that we cannot affirm the antecedent from the presence of the consequent. So just because if we say if it rained, then the earth will get wet, and if I say, well, it did not rain, then that doesn't mean that the Earth did not get wet. Like we discussed earlier, there's all sorts of other reasons why the Earth could have gotten wet. And for the same reason that we cannot confirm that it rained just because the Earth was wet, we cannot affirm that it did not, that the Earth did not get wet just because it did not rain. So be careful not to do this. The modus ponens and modus tollens only work on in certain ways on certain parts of a conditional, and don't mix them up because you end up applying the rule in an invalid way here, and then that would make. So if you did this in a proof, you would get points off for that. But depending on how early in the proof you did it, it would probably, well, almost certainly throw off everything that you do that would follow from this afterwards. So you would want to. You could lose a lot of points basically if you end up doing this. So be really careful about applying these rules. If you apply them in the wrong way, it throws off everything that you do after that that's going to build on the correct application of these rules. All right, so here are some examples. The question is, which of the following are genuine substitution instances of modus tollens? So we can see number one, we have a conditional. If it is the case that Sn not P, then it is the case that Q, if and only if T. And our second premise is it is not the case that Q, if and only if T. So therefore, we can conclude it is not the case that S and not P. This is a correct application of modus tollens. We've negated the entire consequent, which has allowed it, or one of the premises is the negation of the entire consequent, which allows us to negate the entire antecedent. All right. Now, I don't remember what I wrote down. Hold on. I'm going to have to pause this and figure out what's going on here. Okay, well, I have no idea what's going on with this, but if you see this strange box here, this is supposed to be a vel. So this is supposed to be a disjunction. I don't, on my slides it's showing up as a vel, but when I go into slideshow mode it's showing up this way. This other vel is showing up fine as is, so I don't know what's going on with it. Anyway, hopefully this is the only situation in which this happens. For the time being, take my word for it that this is a vel. So this is the antecedent of this conditional is a disjunction between S and P, Sn not P, or if R then C, and the consequent is Q if and only if T, if and only if not D. Our second premise is, well, it is not the case that Q if and only if T, if and only if not D. Therefore, we get the entire first premise, we get the entire antecedent of our first premise negated, S and not P, or R, if R then C. All right, number three. Here, the antecedent of our conditional is D and T, if and only if not D. If D and T, if and only if not D, then it is not the case that S and not P. Our second premise is it is not the case that S and not P. And then our conclusion is listed as D and T, if and only if not D. This is incorrect. So this would just be an example of affirming the consequent. We can see that our second premise here is not a negated consequent. It's just the exact consequent that we had in the first place. The consequent was originally a negation. So if we wanted to apply modus tollens in this case, we would need to have another tilde in front of it there. We would need, it's not the case that it's not the case that S and not P. And then that would allow us to get a negated antecedent. And here the conclusion that we're looking for is not the negated antecedent, it's just the antecedent. And because we can't conclude the antecedent by affirming consequent, we can see that the consequent there, that doesn't tell us anything about whether or not it's also true that D and T if and only if not D. So number 3 is not a genuine substitution instance of mode stolens. Okay, next is the disjunctive syllogism, which applies when we know that two things could be true. In this case, alpha or beta. We know either alpha or beta. That's our first premise. And if it is true that alpha or beta, and our second premise says, well, it's not the case that alpha, then we conclude from that information, well, then it must be true that beta, because we know that either alpha or beta has to be true, and we know that alpha is not true. That's all the information that we're given. Then what we're left with as an option is beta, so beta has to be true. Pretty simple disjunctive syllogism. So here are a couple of examples. So in the first instance, instead of alpha and beta, we have not exactly complex well-formed formulas, but a little bit more complex. We have A and B, or C if and only if D. We know that it's not the case that A and B, therefore we conclude C if and only if D. Whenever we have a disjunction as one premise, and we have the negation of one of the disjuncts as another premise, then it's possible for us to conclude that the other disjunct is true. Our second example here is, if it is the case that A and B, then it is the case that C if and only if D. Well, we know it's not the case that A and B. So can we conclude C if and only if D? No. Well, first of all, here this is a conditional, so it's not even a disjunction in the first place. And second, with a conditional, just because the antecedent is true, just because the antecedent is not true, doesn't mean that it doesn't tell us anything about whether or not the consequent is true. So we can't conclude C if and only if D from the negation of the antecedent of the consequent. If A and B, then C if and only if D. All right, number 3. We know that either A and B or C if and only if D. We know that A and B, therefore C if and only if D. Now this doesn't work either, because, well, first of all, we're using an inclusive disjunction, which makes it possible for C if and only if D to be true at the same time as A and B is true. But we only know that either A and B is true, or C if and only if D is true, or they're both true. But it's possible that it could just be A and B that's true, and C if and only if D need not be true. So we cannot conclude C if and only if D just from knowing that A and B. We also can't conclude that it's not the case that C if and only if D, because it is an inclusive disjunction. It's possible that C if and only if D could also be true, unless we had some other part of our argument that made it impossible for that to be the case. But because none of the disjuncts are negated here, that doesn't tell us anything certain about the other disjunct. We need one of the disjuncts to be negated in order to know that the other one is certainly present. All right. The next one that we're working with here is hypothetical syllogism. So here we can see we kind of have a chain of conditionals going. Our first premise is if alpha, then beta. Our second premise is if beta, then gamma. So we can conclude from that, well, if alpha, then gamma. We're kind of just smashing these two conditionals together here. We know that if alpha is true, then beta must be true. And if beta is true, then gamma must be true. So because any instance of alpha will chain all the way to, certainly, an instance of gamma, because alpha entails beta and beta entails gamma, we can shorten this to just showing if alpha is true, then gamma is true. So this just lets us smash two conditional statements together to, if one conditional statement has a consequent that is identical to the antecedent in another conditional statement, then we can take the antecedent from the first conditional statement and connect it to the consequent of the second conditional statement using a horseshoe. Let's work with some examples here. So which of the following are genuine substitution instances of hypothetical syllogism? So in the first example, we have if A and B, then C if and only if D. Our second premise is it's not the case that C if and only if D, therefore P or Q. And the conclusion is if A and B, therefore it's not the case that P or Q. Now this doesn't work because you can see that in our second premise, the antecedent of our conditional statement is not identical to the consequent of the conditional in our first premise. C if and only if D is very different from it's not the case that C if and only if D. In fact, they're complete opposites. Literally, logically speaking, they're mutually exclusive here. So, because that's the case, we can't connect these two conditional statements together. We can't chain them together. And if, just for example, if the antecedent in the second conditional was just C if and only if D, it wasn't negated like you see here, then we would be able to get to something like A and B. If it's the case that A and B, then it's the case that P or Q. But for some reason, the conclusion that we're being shown here has P or Q negated, which who knows where that comes from. In any case, number one, no idea what's going on there. Not a genuine substitution of, not a genuine application of hypothetical syllogism. All right, in our second example, we have A and B, or C if and only if D, and C if and only if D, or P or Q. And we can conclude A and B, or P or Q. Now again, not a substitution instance of hypothetical syllogism. In this case, well, we're not even using conditionals. Here, the major operators of each of these premises are disjunctions. So just because one of these, either A and B or C if and only if D has to be true, and it's the case that C if and only if D has to be true, or P or Q has to be true, doesn't tell us anything about, well, either A and B or P or Q are true. It could be the case that it's just C if and only if D that's true, that's making both of those disjunctions true. And so it might not be the case that A and B or P or Q is true. So that's not a genuine substitution instance. In the third example here, we have if A and B, then C if and only if D. And our second premise is if C if and only if D, then P or Q. And we conclude, therefore, that if A and B, then P or Q. This case works. We can see that the consequence in our first premise is exactly the same as the antecedent in our second premise. So we can end up just taking the antecedent from our first conditional and connecting it to the consequent of the second conditional, removing C if and only if D to get to our conclusion, which is if A and B, then P or Q. All right. So to construct a derivation, we're going to number all of the premises and any subsequent well-formed formulas derived from them. So this is how an argument is going to look when you're first presented with it. So this argument has three premises and a conclusion. The conclusion is it's not the case that A and B, and the conclusion is going to be written after a slash following the last premise. It'll be on the same line as the last premise. But it's important to remember that the conclusion is not actually part of the last premise. The conclusion isn't really part of the argument at all, except insofar as it tells us something. If we're interested in showing the conclusion from the premises, then we're given a target to try to find with our rules of inference, rules of equivalence, etc. But it doesn't materially contribute to the premises in any direct way. It's off to the side, separated by a slash, That's the conclusion that we're trying to show. And then we'll have our premises listed 1, 2, and 3. And then in each of the following rows, when we want to apply a rule, we're going to add a number, and we're going to write down the new line that we get by applying a rule in some case. So the goal is to apply the rules to the premises to derive new well-formed formulas, ultimately to reach the well-formed formula that is the conclusion. So we have our argument starts with just these three premises. The first premise is if A and B, then C. Our second premise is it's not the case that P or Q. Our third premise is if C, then P or Q. So we can, using just these premises, we can see, well, we can get to a new well-formed formula here. Using a hypothetical syllogism on lines 1 and 3, we can get to if A and B, then P or Q. Now, when we write a proof, when we do a proof like this, any of these lines that we add, we're going to add new premises that follow from the original premises that were given. We have to, off to the side here, show our justification for getting to the new premise. So one of the easiest ways to make a mistake when doing a proof is to write down the wrong lines or the wrong rule that you used to get to the new premise from the old premises. It's extremely important that you be very careful about showing exactly what lines you're using and what rule you're using. In addition to this, it's very important that you only ever apply one rule each time you add a new line. This is going to be really annoying, maybe, and it might be tedious, but the point of a proof is to show concretely exactly how to get from the premises without any skipped steps to the conclusion. And you're going to want the reader, in this case me, especially in this case because I'm going to be grading your work to see if you did it correctly. But also if you're not very careful by showing exactly which lines you're using and exactly what rule you're using, and you're only applying one rule, and to make sure you're only applying one rule at a time, if you don't do those things, it'll just be difficult to follow. If you skip steps or you reference the wrong line, it won't be something that someone will be able to follow. And we're trying to show directly that some conclusion follows necessarily from these premises. So you want to be very clear when writing out each of the new well-formed formulas that you're able to get to from the previous premises in a proof, and to show exactly what lines of the proof you referenced in order to get the new well-formed formula that you created, and what rules you used in order to do that. Okay, so the first step that we can apply here to this argument that we're given, which is originally 3 premise, we add a 4th premise, which is this new formula that we were able to construct using a hypothetical syllogism on lines 1 and 3. Yeah, so we have our justification here. In the book and here in the slides, you can see that for each of the rules of inference and rules of equivalence, there'll be a sort of shorthand version of it. Modus ponens is MP, modus tollens is MT, disjunctive syllogism is DS, hypothetical syllogism is HS. So, well, you don't have to write out the full thing. You can use a shorthand like this, and we'll be showing, whenever the rules are introduced, the shorthand will be introduced as well. Okay. So, from here, on line 4, you may have already seen how to complete the proof, but the conclusion that we were trying to show is that it's not the case that A and B. If we're able to get to, on line 4, we're able to get if A and B, therefore P or Q, using 1 and 3 with hypothetical syllogism. Well, if we look, we can see on line 2, well, it's not the case that P or Q, and if we apply that to line 4, we get the negated antecedent using modus tollens. So with lines 2 and 4 modus tollens, we're able to write down a new well-formed formula here. It's not the case that A and B, and it turns out that, well, not A and B is the conclusion that we were trying to show, so we're done. And so it should show this in the book. QED stands for quoterat demonstrandum. It's something that you write just at the end of a proof to sort of clearly indicate that you're done. It means that this has been shown or this has been proven, something like that. So when you're finished with a proof, when you've shown the conclusion, go ahead and write QED. That just indicates that you didn't stop halfway through, that you understand that you've arrived at the conclusion, and you've been able to derive that from the original premises. Okay, here. The QED stuff, yeah, technically not part of the proof, but it's just something to sort of signal that you've done your job there. Okay, so many arguments have more than one possible derivation. There's different ways that you could do things, different rules that you could apply to get to the conclusion in different ways. Any correct application of rules, it will be fine. Although you may find that in looking over the homework videos, when I am solving the homework questions in a certain way, it might be different from the way that you solved it, in which case it'll be important to look at whether or not you applied the rules correctly for those. And if you did, then it would be a correct answer. That's fine. And usually you'll have some sense of whether or not you did things correctly. Things will go off the rails usually if you do something wrong. But if you're familiar with what the rules of inference and the rules of equivalence are, you're comfortable with what those are and how to apply them, then even if your answer is different from mine on the homework assignments, that doesn't mean it's necessarily incorrect. But you might want to go ahead and mark somehow the different answer but correct on your homework assignment when you're correcting those. So the proof that we just did, here's an example of a different way that we could get to the correct answer. So the original proof is just these first 3 lines. And then after that, we'll be applying rules in different cases. So we can see that we could just go ahead and apply modus tollens to using line 2 and 3. We already have a negated consequence for a conditional there, so which means we can arrive at the negated antecedent of that conditional. And if we have the negated antecedent, in this case not C, that turns out to be the negation of the consequence of a different conditional, which is our first premise. So we're able to work backwards with modus tollens to get to it's not the case that A and B. Where if we use hypothetical syllogism first, we just smash these 2 conditionals together, and then we use modus tollens. But this way, we just work backwards through the chain of conditionals instead of using another step to move them together. And you can see it takes the same number of lines. Generally, if you can do things in fewer steps, it's better to do so, but a proof with more steps is not going to be less correct than one with fewer steps. You might be interested in doing fewer steps just because, well, this stuff can get tedious, especially with some of the rules of equivalence that we'll introduce later, where we're going to be doing a lot of, there's a lot of rules that you'll wish you could skip, basically, but it's important to actually take the time to write them out on their own line. But in this case, either way that this was solved would be perfectly acceptable. Something that's not acceptable, however, is trying to use rules of equivalence on only part of a line. So you can see here that we have a conditional if A and B, then P or Q. In our second premise, we have not P. We can't get to Q from there. If we had a line that just said P or Q and we had another line that said not P, then sure, we could get to Q no problem. But here, the disjunction P or Q is just part of the consequence of um, a conditional, which is just expressing the relation between if A and B, then P or Q. Um, we don't have enough material there, and also just it's going to be nested in these larger operations that uh, don't allow us to just pick out part of the well-formed formula that we're dealing with. Um, rules of inference can only be applied to whole lines, or whatever the major operator is going to tell us what rules of inference we can use on that line. Okay, so when we get to rules of equivalence, that'll be a little bit different. Rules of equivalence will work on part of a line because it's replacing a well-formed formula with something that's logically identical to it. So that would be okay, but with rules of inference, it's something that we can only do on entire lines. All right. So here's some more rules of inference, leaving behind the conditionals for a second. First is conjunction. And we'll shorten this with just conj here. So you can write that when you're using this in a proof. So if we have one premise that says alpha, and we have another premise that says beta, well, we can conclude alpha and beta. Now this should be fairly obvious. If it's true that alpha and it's true that beta, then it's true that alpha and beta. This just allows us to put these both on one line and express them as a conjunction. Yeah, this one's fairly straightforward. If you have one thing and you have another thing, then it's true that you have one and two. You have both things. So conjunction is just a way to express that. Now, it's the difficult thing about conjunction is that it's often confused with this next rule. So the next rule of inference is called addition. Now people are often tempted to call conjunction addition because it looks like we're adding A and B together. It's very important to remember that addition is a completely different rule that applies to disjunctions, and conjunction applies to conjunctions. Hopefully the name should help you remember that when we want to take two things that we're already given and connect them using and, A and B, we want to say it's true that A and B. The rule that we apply in this case is called conjunction. Addition is something completely different. So addition is when we add something to something that was already given using a disjunction. Very important that we use a disjunction here, the vel, and not a conjunction, the dot. So here the only premise we have is alpha, and from alpha we conclude alpha or beta. Now this is because, well, we know that a disjunction is true when one of the disjuncts is true. In this case, we know that alpha is true. So we know that it's true that alpha or beta. We don't know whether beta is true or not. We don't even know what beta is, necessarily. But we know that alpha or beta as a statement, overall, is true, because alpha is true. So it's true that either alpha or beta. This is a little bit unintuitive, but the important thing to remember is that we use the OR operator. If we tried to say alpha and beta here, well, we wouldn't be able to do that because we would need to be certain of the truth value of beta in the first place in order to say it's true that alpha and beta. Here we only know that alpha is true, so we can say alpha or beta is true because we know that alpha is true. So yeah, so be careful with this. Addition can only be used with the vel, the or operator, the disjunction. It cannot be used with the dot, the conjunction. So an example here, just because we have apples doesn't mean we have apples and bananas. But because we have apples, it does mean that we have either apples or bananas. It's true that we have either apples or bananas. So this one's a little weird. Addition may feel like cheating since it allows us to add any and every well-formed formula to any other previously established in the argument. So if we have one premise S, well, the second premise, I can add whatever I want to it. In this case, I can add this rather long formula and I'm just gonna, the justification is premise one, addition, I'm taking S and I'm saying, well, either S or C if and only if D or not Q. If it's the case that C if and only if D or not Q, then it's the case that A and B or not P. And that'll be true because S is true. So it's true that S or this other long formula. So, for example, if it's true that salt contains sodium, then it's true that either salt contains sodium or pepper contains pumpkins. One of those two things has to be true, and because I know that salt contains sodium, the statement overall is going to be true, even if maybe it's less completely true than the statement by itself. But as far as the truth value of the disjunction goes, it's true. All right. Next is simplification. So this works in kind of the opposite way of conjunction, where we know that if we have alpha and beta, well, then it's true that we have alpha. So, yeah, alpha's, to say alpha and beta means it's true that alpha and it's true that beta. So, therefore, it's true that alpha. These two things aren't relying on each other in any way. We're just expressing that they're both present. So that means that any one of them individually is present. So be careful with this. So simplification can only be used with the dot operator. It cannot be used with the val. If I know that if I know that alpha or beta, I can't necessarily conclude alpha from that because I don't know if alpha is the part of the disjunction that's true. It might only be beta that's true. So if we have either apples or bananas, it doesn't follow that we have apples if I don't know it. But if we have apples and bananas, well, from having apples and bananas, I can conclude that we have apples. But if I only know that we have one of them, but I don't know which one, I can't conclude positively that it is one or the other of them. So simplification can only be used with the dot. All right. Next rule of inference, constructive dilemma. This one is a little bit weird because it applies to 3 lines in a proof rather than 1 or 2 like most of the others. So constructive dilemma, or CD, is a rule of inference with this form. If we have 3 things, we need 2 conditionals and a disjunction here. First, we have if alpha, then beta. Then we have if gamma, then delta. We can then conclude, and then the third thing that we need is either alpha or gamma as its own line, as its own premise. From this, we can conclude beta or delta. Now, if you think about this for a second, well, we know that if there was an alpha, then there would have to be a beta because of the first premise. And we know that if there was a gamma, then there would have to be a delta because of the second premise. We know that there's either an alpha or a gamma, but we don't know which one. Because there has to be at least one of them, then we know that at least one of the 2 antecedents is true. We don't know which one, though. And if one of the 2 antecedents is true, then we know that one of the 2 consequents would have to be true, would follow from the conditional that's expressed there. So if we have 2 conditionals as different premises, and we have a disjunction where each of the disjuncts is one of the antecedents of the 2 conditionals, we can conclude from that a disjunction that has each of the disjuncts as one of the consequence of those conditionals. So if it is true that if alpha then beta, and it's true that if gamma then delta, and it's true that that alpha or gamma, then it's true that beta or delta. One of these two consequence has to be the case because one of the two antecedents is the case. Right. So here's some examples of using these rules of inference in derivations. So your homework assignments are going to look like this, where a lot of them you'll be given an argument. Here, this is an argument with 3 premises and then a conclusion here. And then you'll be asked to derive the conclusion from the premises. So the first premise is if S or P, then not G. The second premise is if H, then G. The third premise is S and P. And our conclusion is not H. So sometimes it can be difficult if it's not obvious to you where to start with one of these, what to do. So one thing to think about to help strategize is to look at the conclusion. See where the conclusion is that you're trying to find and see if there's anywhere that you might be able to get there with the premises. We can see that H only shows up in the second premise in this argument. And H here is the antecedent of a conditional. Well, we know that one of our rules allows us to get a negated antecedent of the conditional if somehow we can get a negated consequent of that conditional. So using modus tollens. So if we can get not G somewhere, then we would be able to get not H. And we see that not G shows up in the first premise, which is S or P. Okay, so a couple of things we can do here. So the first thing we can do is we'll simplify from our third premise, S. So we want just S by itself because the first premise is saying we need S or P in order to get not G. And the third premise says we have S and P. Now you might think it's obvious to you that if you have S and P, then it means you have S or P. But when we're doing a derivation, we need to explicitly get there just using rules of inference and rules of equivalence and make it obvious to any viewer that there is just using logical steps that we can get there without having to rely on our intuition to kind of bridge any gaps. So that might be frustrating to see that, well, the third premise you have S and P, and the first premise you have S or P. So it should be obvious to you that there's a not G that we have in play, but we need to get there using steps. But luckily in this case, because we have S and P, it's trivial to get S or P. Because, well, first we'll just simplify the S out of the S and P. And then we can use addition to get S or P. We could use anything here if we wanted, if we needed S or Q, if we needed S or W, if we needed S or Z, whatever it was, we could use addition to get there. In this case, it's P. So we'll go ahead and use addition to add or P to the S, because remember, we know the S is true, so S or anything is going to be true. So because we have S or P then, we're able to apply modus ponens to lines 1 and 5. Remember, keep in mind that rules like modus ponens that you need to reference 2 lines for. It's very important to have both lines in your justification. You can see in premise 4, we only needed to reference line 3 because we were just simplifying part of line 3. And in premise 5, we only needed to reference line 4 because we're just adding something to the entirety of line 4. But because modus ponens requires two things, one, it requires a conditional, and two, it requires a separate line that has the antecedent of that conditional, we need to reference both of those lines in any application of modus ponens. So here we're able to get not G from lines 1 and lines 5, where line 5 contains the antecedent of the conditional in line 1. So because we have not G, now we're able to get to not H. If we apply modus tollens to lines 2 and 6, so we have not G in line 6, which means that using modus tollens on line 2 and 6, where we get, well, line 2 says if H then G, and we know that not G, therefore, modus tollens line 2 and 6, we get not H, and because not H is our conclusion, we're done. So we can write QED, and we're finished with this proof. All right, let's do another example. So here we have 4 lines in our initial argument. The first premise is if S and P, then R or Q. Our second premise is S. Our third premise is not R. Our fourth premise is P. And our conclusion is Q or D. Now, in a situation like this, it might not be super obvious how to, well, it might be because this one's pretty simple, but sometimes you'll run into arguments where it's not super obvious how to get the conclusion from the given premises. Whereas before we looked at the conclusion and we just looked for the conclusion in the premises, and we're kind of able to work backwards there come up with an idea of how to arrive at the conclusion. If it's not super obvious, something that you can do is if you see any obvious rules of inference that you can apply, given the premises that you have, go ahead and do those, and you'll get new well-formed formulas that might sort of jog your intuitions a little bit and give you a sense of what to do. In this case, we can see that, well, we have S and P on different lines. If we use conjunction to put them together, that would give us the antecedent of a conditional, which would give us the consequence of the conditional on its own line. We would have more material to work with. Therefore, then we could get the Q by itself, and then with addition get Q or D. Well, that's sort of the whole thing, but we'll go through that one step at a time. The first thing we can do is, well, on line 2 we have S, line 4 we have P, so we'll go ahead and put them together. So we have 2 and 4 conjunction here, S and P. Now, because we have S and P on one line, we have the entire antecedent of our conditional on one line. Now we're able to use modus ponens. So with 1 and 5, if we have S and P, then we have R or Q. On line 5, we do have S and P. Therefore, we can put on a new line R or Q. Our justification is lines 1 and 5, modus ponens. Now we can conclude Q, because on line 3 we have not R. So if we know that it's true that R or Q, and we know that it's not the case that R, and either R or Q must be true, then Q must be true. So line 3 not R, and line 6 R or Q give us Q with disjunctive syllogism. And lastly, because we have Q, we can go ahead and use addition to add Q or D. We know that Q is true, so Q or anything else is going to be true, because one of the disjuncts, in this case Q, will be true. So we can, so there's a mistake here actually. See how easy it is to make a mistake on these. The justification for line 8 here reads 8 addition, but it should read 7 addition. I'll go ahead and fix it after flagging that there was a mistake here. Okay, so went ahead and fixed it. So the mistake was that On line 8, I wrote line 8 as the justification, but the justification should always reference the lines that you're applying the rules to. In this case, we're applying addition to line 7, which 7 was where the Q is by itself. And to line 7, we're adding something, in this case, the D. So that's something to watch out for. But on line 8, after we've done that, we have Q or D. We can see that Q or D is the conclusion that we were trying to show. So we're done. All right. Yeah, in the next one we'll talk about rules of equivalence. This is all for rules of inference.